Hi, I'm Boyd. I'm in the contingent of people in this room that have come a very long way to be here. It's 2:30 in the afternoon and my body thinks it's 2 in the morning. So I'm 11 time zones off and I'm feeling it right now. That's an interesting point. There's a lot of people in this room that have come from the other side of the planet. And it says something about the fact that they traveled here to talk to you guys and to be in this room today. There's something really interesting going on that we are all collectively working on. And that's part of what I'm going to try to put my finger on today, is why are we here and what are we trying to do? And I honestly believe that this community is at a turning point. And to me, the question is, are we going to build a bunch of academic research projects that eventually fizzles out? Or is this going to become something that takes off? And when I say takes off, I mean is on millions and millions of devices, that becomes a critical part of our infrastructure, that is something that the world depends on and relies on. And I honestly think we're going to get there, and that's why I'm here. It's too important to not take this seriously. So that's what I'm here to talk about. This is not a technical talk. This is about where this community is going and some of the impact we can and could have together. Now, as I look around the room, I see roughly 3 different communities represented here. And it's the same as last year, same as the year before that. There's not enough people in the room, but it's still roughly the same 3. There's research, fundamental research that's going on, and that's absolutely critical to the space that we're in. There's people like Kry10 and like Neutrality that are building operating systems that are intended to be platforms that can be used more widely. And there's people whose end goal isn't necessarily the systems and the proofs and all that. They're here to build devices and ship systems. That group changes year to year. It's a different crowd each time, but they're the end customers. They're the ones shipping actual devices. And I ask myself, what's the common thread that binds us together? And that's part of what I want to talk about. And even if I end up saying things that are somewhat challenging, partly because I'm so jet-lagged, this is intended to be a message of hope, not just for the community, but for the state of software development in general. And I really mean this. So yeah, the title, Science, Engineering, Craftsmanship, Magic. It's a subject I've been thinking about for a long time, and I've been trying to develop some thoughts around it, and it helps give me framing for what we're trying to do together. So let's start by defining those 4 words, and then we're going to see how do they apply to the world of software, and that'll help me understand what we're actually trying to accomplish. So science, what is science? Right, science is discovering the world as it is, without bias, without intent. You know, you hear the joke about the mad scientist wanting to blow up the world. It's never a mad scientist. The mad scientist would blow up half the world and leave the other half as a control group. Right, it's always mad engineers. A scientist is trying to discover the things that are. They just are. And that can be in math. I put Pythagorean's theorem up because to me that's science. It's a fundamental. It's a concept about the world. And whether it's quantum physics, it's atoms, it's physical things around us, or if it's mathematical concepts, that fundamental research to me is science. Okay? So what's engineering? Let's look at the 2 buildings. The one on the left is Hampton Court, which was King Henry VIII's favorite palace, built by Sir Thomas Wolsey. Actually, I don't know if he was a Sir. Built by Thomas Wolsey in 1515 to celebrate his becoming cardinal. It was then basically stolen by King Henry VIII, who liked it better than his palace, and he lived there for a long time. That building was built 100 years before Leibniz and Newton co-created calculus. They didn't have math. They used best practice. They used shared knowledge on how to build that building. Now compare that to the building on the right. That's student housing in Christchurch, New Zealand. In 2011, Christchurch was pretty much flattened in an earthquake. A lot of people died. And when they rebuilt, they have done a ton of math and engineering on that building to thoroughly understand the vibrational frequencies of the structures, to know how it's going to work in various earthquakes. A whole bunch of the buildings built in Christchurch now are rated to survive a 9-point earthquake. Okay, there's a difference between engineering and craftsmanship. One on the left to me is craftsmanship, the one on the right is engineering. And I think that engineering was pretty much born when Newton and Leibniz created calculus, right? It gave us the fundamental tools to build evidence of correctness. And to me, that's the key thing about engineering, is you've got evidence. And that evidence is based on the things we learned from science. So what's craftsmanship? Craftsmanship is the act of creating things and creating solutions to problems, but without evidence. We do it when we fundamentally use best practices, experience that we've gained ourselves, experience that we've learned from people who taught us, but we fundamentally don't have proof of correctness. Now, you can make beautiful things with craftsmanship. Notre Dame, to me, is a great example. It's a beautiful crafted building. I really don't think they had calculus when they figured out the flying buttresses. Trial and error, lots of experience. They created an absolute masterpiece. Video games are largely not provably correct. You don't know if something weird is going to be fun or not. And then my favorite example is somebody made a hot dog and pickle Jell-O. Now, is it good? I don't know. I'm not going to try it, right? But you can't prove it's good and you can't prove it's bad. To someone, it's art. It's craftsmanship. Right, so really understanding the difference between craftsmanship and engineering is really kind of what got me to where we're going. Now think for a second on where software fits into that picture. Is software engineering or is it craftsmanship? And we'll get to that in a couple slides. But first, what is magic? Now I really like this quote from Arthur C. Clarke. Any sufficiently advanced technology is indistinguishable from magic, which leads me to my definition. Magic is the use of tools created by engineering or craftsmanship without an understanding of how they work. Right? You're solving problems in your life, you're using the tools that were given, but you have no clue how they actually work. Well, that's magic. You trust that they work. You hope they work as they're supposed to work, but you don't know. When most people get in their car and they drive it down the street, they know the magic spells to make it move forward, the magic box, right? There's one pedal that makes it go, and there's another pedal that makes it stop, and you turn the wheel to turn. Those are all spells. They memorize how to do it. Most people don't think what's going on inside the car. They're not thinking about combustion. They're not thinking about power coming from the batteries or the motors. They don't know how any of that stuff works. Let's go with another really practical example. Do magic wands exist in the real world? Absolutely, yes. Lots of people have TVs and they have a remote control, and that is a perfect example of a magic wand. Right, here's a stick. You don't understand what it does, but you've memorized spells that you push into the buttons, and then the thing on the wall magically comes to life. You see pictures from faraway places. You can interact with people at a distance. 100 years ago, that would have been flat out magic. Now, we know there's engineering behind this stuff, but the people who use it don't understand that. Now, think about software. Every API that you call that you haven't studied the code behind it and you don't know how it works is effectively a magic spell. Right? We live in a world of exaggerated wizardry. Right? We have to memorize vast amounts of APIs, vast amounts of spells. We don't look at the code behind them. We don't study them, and we hope that they work. The problem is that 99% of that stuff, actually it's probably like 5 nines of that stuff, is crafted. It's not engineered. And there was a point when I was sitting thinking about this, and I'm like, you know, my degree from too long ago now, my degree is mechanical engineering, right? And we studied engines and gears, and there's lots of rules in how you do it. In lots of engineering fields, like building buildings and all that, you have to get a license. You have to prove that you know what you're doing to be allowed to design bridges and buildings. And that is just so not how we build software, right? And then at some point I realized, oh my gosh, all the people that I worked with at Microsoft, I didn't give my background. I was at Microsoft for 18 years, I worked on Xbox, blah, blah, blah. All these people I worked with who all call themselves software engineers are not. They are not engineers. They're all craftsmen. There are very few software engineers. And some of them are in this room. So if you think about the history of software development, it is all craftsmanship. You learn from best practices, you learn unit tests, you write a bunch of code, you test it a bunch of different ways, you hope it works. Right? That's craftsmanship. I'm going to say there's 2 revolutions happening in software right now, and they're both changing everything. The first one gets all the attention and all the money, and that's AI. AI is truly different. It is truly a new way of creating logic and creating software. It's not logic, right? You're training giant tables of matrices, lots of learning processes and reinforcement learning going on, embedding tables, blah, blah, blah. What we're moving away from is predictability and repeatability, and you're getting some really interesting decision-making coming out, but you don't know that it's correct, and it's almost unprovable. When you have that much complexity in a bunch of tables, you can't go backwards to show that the decision that came out was the right decision. But it can be probably right. And in very complex cases, it can be almost miraculous. It is the definition of magic. Even the people who build the models don't know how they work. Right? It's sorcery. It's not wizardry, it's sorcery. The other revolution, which I firmly believe is just as big, but not well known, and the story has not been well told, is I used to have formal reasoning, formal methods up there, and in a lot of my conversations with people, it's like, please don't call it formal methods. It doesn't sell. Call it automated reasoning. But it's effectively all the proofs that we've been talking about. That's in the field of automated reasoning. And eventually what you realize is what we are really doing, and when I say we, I mean the collective we. I don't mean Kry10. I don't mean the SEL4 community. I don't just mean the people working on the Cyber projects. I don't just mean the Byron Cook Amazon proof team, like 600 people, what? 1,000 now? I don't know, I'd believe it. I don't just mean all the people working on cryptography. You take all these groups together, and what we are creating is the field of software engineering for the first time. If you can define software in a proof, and you have evidence that it's correct, and then you build a bunch of C code or whatever, and you link that back to the proofs, what have you done? You've just engineered logic. Not through craftsmanship, but through engineering. And that was a moment for me when I'm like, oh, this is interesting. One of those moments was I've been using Pythagorean's theorem a lot to try to explain to people who don't know what I'm talking about what the heck I'm trying to do. Right? If you go around to VCs and you're pitching to companies that make industrial equipment and they have no idea what a proof is or what formal methods are and what automated reasoning is, it's a really hard story to tell. It really is. We're finding much more success talking to people who already get it. They're already in the field. So I've been using Pythagorean's theorem, and there's a shift that happened in my mind at some point. It's like, okay, a squared plus b squared equals c squared. We all know it. It's like the first proof I ever learned. It's maybe the only proof I ever learned. Whatever, right? The shift that happened for me was to realize, wait a minute, it's not just a proof of something abstract. It's actually a spec for a right triangle. And you can take that proof, and what it means is that I can give you any three numbers. And you can tell me yes or no, that describes a right triangle. Right? The theorem itself is actually a spec for a right triangle. And I can use that. When I think about Hoare logic, and I think about what the theorems that this group is trying to build, it's effectively the same thing. The theorem is the spec for the software. And then there's a whole lot of work in tooling and other things to map the actual software back to the spec, which is in the language of math. I live in New Zealand now, maths. Fundamental shift in my head. And that's what led me to software verified by automated reasoning is engineered software. And this really is a fundamentally different concept. And part of what I'm trying to do with this group today is when we are done, and you're off outside this community, and you're talking to companies, you're talking to people who aren't academics, you're doing whatever, we have a message we need to consistently talk about. Because the rest of the world needs to understand that software engineering can be a real thing, and it is fundamentally different, and it does change the rules, and it does let us do things we can't do today. Right? And almost nobody who writes software today is an engineer, except maybe in cyber defense and cryptography, and Gerwin. Right, so what? Who cares? Maybe craftsmanship is good enough. Alistair over there with the camera. Wave your hand. Alistair's here. I asked him to come here. I wanted to get some other communities exposed. He's the head of the Erlang Foundation, the chairman of it. I'm a big fan of Erlang. It teaches how to do error recovery. It teaches a whole bunch of things. It doesn't have any formal methods at the bottom, but it's got a community of people who think in terms of error recovery. Getting that community mixed in with this community, I think, is a good thing. When I was at the Elixir conference, which is effectively an Erlang conference in Krakow a couple months ago, I've been traveling way too much this year. There were a couple thousand people there. Those are the numbers I want to see. I want to see 1,000 people at this event, 2,000 people. And we have to get there. We have to cross some of these communities. Talk to Alistair. He was at the Linux conference last week. Lots of people there. When they talk about higher assurance, higher trust, they're talking about Zephyr. There's still no formal methods at the bottom, but that community is going to end up latching onto something that is inferior, and they're going to start running with it and building momentum and building inertia. And we have to figure out how to get our messaging straight and actually make some progress in the face of a world that doesn't understand what we're doing, and they are starting to run in a, frankly, wrong direction. All right, so craftsmanship, is it good enough? No, it's not. Not for critical systems. Not for safety systems. We'll talk about open source for a sec. This is the problem with engineering. Engineering's expensive. You have to get degrees to be an engineer. Sometimes in other fields, you have to get licenses to be an engineer. You have to pass effectively a bar exam to be an engineer in other fields. If we're talking about engineering, and we're talking about safety critical systems that people die if they fail, why do we just let anybody write anything? to put on those systems? Right? Why don't we require engineering? And if you do require engineering, that's expensive. How does that get paid for in a world where everything's free? It's a hard question. Now, free, lots of contributions, all that stuff, it makes perfect sense in a craftsmanship world, where you got a bunch of craftsmen who don't necessarily have evidence behind them all contributing to something, where you don't necessarily have great controls and long chains and looking for supply chain attacks and all that kind of stuff. This is a fundamental thing that comes out of that kind of thinking, and it's okay. But maybe we have to rethink it a little bit in an engineering world. You know, most of the world, like in the US, if you write software and that device fails and people died, so what? There's no liability. The laws in the US, at least in parts of the US, are like, yeah, whatever, it's software. You can't, there's no way to have it be right. No liability. That's changing. The European Cyber Resilience Act is starting to assign liability. The US is considering laws to assign liability. Right? We're slowly moving toward a world where that software is going to have consequences on it, and that's going to require people to start doing engineering. Right? And then when we talk about bringing engineering to the current software world, it's hard. It's a hard sell. You have to change your practices. You have to learn a bunch of hard new concepts. It's part of why there aren't that many people in this room. But we are the leading edge of it. And we have a message that we can bring out to them as to why this is a worthy thing to do and why this is important. I thoroughly believe that transitioning to software engineering is inevitable. It just is. We live in a world where devices that have smarts on them, or maybe AIs on them, are proliferating. They already are proliferating, and it's going to accelerate, and they're going to be everywhere. Do we want to live in a world where there's a device that's bringing power to this building that's got an AI on it that's running on Linux? I don't. I know what's going to happen. It's going to get hacked by Volt Typhoon. There's going to be something that triggers that attack. They're going to cause a fire. We're going to lose a substation. City goes dark. Right? Do you really want to be in a place where there's no water for weeks on end because they didn't shut down the pump? They overdrove it and broke the pipes? That's the world we're looking at. That's what Cold War 2.0 is, by the way, is that everybody has so attacked everybody else's fundamental infrastructure that in the space of a couple minutes, you can completely shut down critical resources for a city. Right? The only solution to this is to engineer the software running on those things. AI just makes it harder. And I do believe that just like the other engineering disciplines, software on critical devices will become regulated. The bar will rise. And the answer to that is the work that we are doing. And I mean the collective we. I think a lot about real-world engineering on software. And this is going to mimic a little bit of what people have talked about today. Like John this morning when he was talking about Hammer, that's really what we're talking about, is how do we describe the structure of a system. In a world where we can really only afford to engineer 1 or 2% of the software on a computer, it becomes very important to pick the right 1 or 2%, the thing that has the most leverage. And to me, that's the structure of the software. It's the containers. It's the lines of communication. That's the piece that needs to get engineered. And that's what drew me to SEL4 in the first place, is because here's a system where I can have proofs down at the bottom of how I arrange the policies and know that those policies at least are correct. Maybe not the arrangement. There's still a lot of research to do on how to do the arrangement and show that the arrangement is done correctly. But at least I've got the basis now of something to build this kind of a system. I'm not an academic researcher. I'm just not. I'm all about practical applications. So I go talk to people. I've got my long list of what customers actually need. They need minimum downtime on their systems. They want to be able to update them while they're running. Highly resilient. You got to be able to recover from failures. You know why electrical utilities don't patch their systems? When you sit down with an electric utility, they don't put patches on their equipment. The main reason is they can't guarantee they can roll it back if it doesn't work. Right? The patch could corrupt the system, the OS on the machine, and now you got a brick. So they don't apply the patch because they can't take the risk. This is why like 20%, 25% of the world's critical infrastructure is still running Windows XP, which blows my mind. These are things that we can address through isolation and through engineered software in the right places. Oh, I missed a really important thing. Like, I'm trying to not promote myself too much in this because I got another point. I'm trying to make a big point here, but we will have our first ISO 26262 safety manual in 2025. That's like 2 years of work. Turns out that stuff's hard. Doing certification is hard, but it's a really important point for the next slide. So what are the things that we need to do as a group? How can we change the conversation? How can we cause engineering backed by formal methods to become, automated reasoning, backed by automated reasoning, to become not just required, but commonplace? Right? And these are just a few things that I think we can do. I would start with embracing certification. It sounds like a burden. It doesn't sound very fun. It's not very fun. It is important. It is required. And it's not enough to say, let's think about how do we do certification of our systems. I want to take a step further. I want to find the people who are writing the certification requirements. In ISO 26262, which by the way is the automotive safety standard, forces you to show freedom from interference between components. Things like if the software in the little ECU on my headlight crashes, it won't lock my brakes. That kind of thing, right? It's actually fundamentally important. And as components come onto a single computer, if the software for my headlight is on the same computer as the software for my brakes, you still need to show that if one crashes, it can't take down the other. But here's the funny thing. In the certification requirements, it says, here's a bunch of evidence you can provide to show that you met it. And the last one is formal proof that you did it right. And then there's a little asterisk and it says not required because no one can do it, right? We should change that. If there is a way to do it, let's make it required. It's going to happen. The question is, does it happen sooner or does it happen later? And can we collectively as a community move this sucker along? Because the faster we get into a world where certification is actually required and verification of it is actually required, the sooner we get into a place where the collective work that we are all doing actually hits scale. I do think we need to think about our language, formal methods, automated reasoning. I think there's momentum behind automated reasoning. I'm open to other names. Let's make that a conversation. I have found it doesn't work to pitch security. If you come in saying that you can build a more secure system, no one gets what that means. You go to a company building industrial equipment and you try to pitch security to them, they're like, what, I haven't had a breach. Why should I pay money for that? You come in talking safety, you talk resilience, that's a language they understand because that equals money. Resilience equals downtime, downtime equals money. Safety equals liability, liability equals money. Those two you can sell. You can't sell security. And look, if you look at previous transitions from craftsmanship to engineering, look at buildings, it took hundreds of years. It didn't become commonplace. You had to have a lot of disasters. Same in electrical, same in every single engineering field. We don't have the time. You look at the attack vectors, you look at the groups that are actively going against our running systems. They are active now. It is pervasive now. And devices with AIs on them are proliferating now. We don't have time. We have to get our story straight. We have to make sure the people who are in a position of authority understand what we're talking about. We can't, how to put it, we can't fall to the temptation of saying that things that aren't ready are. I tend to be very careful to not announce things before they're good to go. We need to uphold this community as a trustworthy community, not just the software. And that means getting our language right. It means getting our commitments right. It means having a straight story to the politicians and to the regulators, and to tell that story consistently so that they understand it, they back it, and they can start to enforce it. Last point. This can't take 100 years. This can't take generations. We have, 5 years, 10 years before there's a massive calamity. That's the path we're on. We have got to move this thing forward. And that's going to require everybody to be on the same page, messaging-wise. Last slide. How do we know we're succeeding at this? What's the success criteria we should be looking for? I want to see a diversity of projects. I loved David Cook's speech today, his talk today. I thought it was great. On the surface, it looks like I'm competing with him. Hey, I'm building an OS, he's building an OS. We're both going general purpose. We're both trying to build on devices. We're not. We're going for different devices, different use cases. There's a lot of use cases, and they have different requirements. And that's okay. That's a good thing. When we see lots of different ways of building lots of different kinds of devices, and we don't pick a monocultural way of going forward, then we have success, because we're going to be able to cover a wider area. The thing I care about is not really how many projects there are, though. One of the bigger success criteria for me is how many devices are active in the field. Right now, that number is not hundreds of millions. Things running verified software that we know of. I don't know, maybe there's 100 million classified devices. I kind of doubt it. I highly doubt it. This table is probably the first ones that are going to hit those kinds of numbers. That's great. That's one device that'll hit numbers. I'm worried about everything else. How do we take the numbers of devices and have it start to be a B with a billion? Because that's where this needs to go. That's what we have to be measuring. And I don't mean a billion devices built. I mean a billion devices active, deployed, and managed. Things that have been integrated into operational centers, things that are actively protecting infrastructure. That's how we know we're succeeding. And then I actually do worry about the health of the community. It's funny for me, because I'm an introvert and I sometimes tend to not participate enough, because it takes work. I know I am an introvert, though. I'll have to hide after this. I've built communities before, right? When I was at Xbox, at Microsoft, I ran the developer community for it. We cared about how many engineers were in it. Craftsmen. How many craftsmen were in the community building games. We worried about code sharing velocity. Think about a lot of the research going on. It's partly about proof sharing, right? What you're doing is taking the burden of building different proofs and adapting them and lowering it. I've got a strong interest in seeing if I build a driver for one system, can I use it in other systems? Right? What's the code sharing velocity while still maintaining the provable nature of the systems that we're on? Very interesting topic. And this community needs to grow 2 orders of magnitude. Full up. It's a little disappointing. I think in Munich there was quite a few more people. Definitely in Minneapolis. I think we can do it, though. We have to get our messaging straight. There's a lot of companies in Europe that should care about this. there should be 1,000 people here, and there can be 1,000 people here, but it's going to be hard, and we have to get our messaging straight. I can take questions. Are you going to be the question master?
Okay, let's start at the right side. Great sermon, thank you.
That's
talk about the certification angle a little bit, and there's a real risk there of malicious compliance, right? If we just go in and like take away the asterisk on the formal methods, formal verification, part of 26262, because you have to have people on the regulator side who are prepared for that kind of evidence, and people who will produce that kind of evidence in a quality way, not a malicious check the box way. I'm not sure what the question is in there.
I'm not either, but I'll repeat the statement.
We gotta. There's a real risk of that blowing up in our face if we go too fast in that direction. I think all the other ways, like, are going to be more productive for, talking money to people, like you were saying, right? You gotta, like, in my world, you have to buy your way onto the airplane. That's the only way to get on. It's going to save money. It's going to
Absolutely.
requirement or something.
The root of the statement/question was there's danger in pushing on certification too soon because some people can game the system, combined with don't rely on certification as a hammer to move things forward. You have to have a carrot as well in the form of saving money. I completely agree. Oh, and by the way, thank you. Yes, it was a sermon, and that was the intent. Look, like DO333 exists. But no one follows it. No one follows it. Why? It's just because they can't do it. What we are creating is the tools and the capabilities to maybe make that thing a requirement.
Wow.
Oh, no, hold on. Let me get to the other side of the point. We don't have to make this up. Other engineering disciplines have paved this way before us. Right? How do buildings get built? How did the codes get done? How do you prevent people from gaming the codes? They do game the codes. They also lose their licenses when they do it.
But they took centuries too.
It did take centuries. It took centuries. But this is the point, there's a subtle point I was making in there of it's not, look, you got to have carrots, you got to have sticks. And then I've been saying, you got to have a carrot, a stick, and a bulldozer that comes from the side and moves the whole thing. Right? What's the carrot? The carrot is I'm going to save you money, I'm going to save you downtime. The stick is we're going to make it required. We change the certifications. What's the thing coming in from the side? Okay, well maybe you have to pass an exam and you have a license to practice on critical safety equipment. I don't know, I'm making that up. Maybe it's a terrible idea. It kind of scares me because I don't want to have to go get it. But maybe that's where we have to go. I don't know, it's a conversation. Give the question and answer.
So I'm curious are we at the point now where we need to start engaging insurance companies?
Ooh, my favorite topic.
Maybe it's certainly going to be something that even before we get to enforcement, it's going to be something that they're probably going to be first movers on that.
Yep.
So do we need to start having the conversations and start getting them to think like that?
Are we at the point, I'll repeat it, are we at the point where we should start engaging insurance companies? I already am engaging insurance companies in this conversation. Yes. Think of it, what we're really doing as a group is we are lowering the risk of devices. We are lowering the risk of a fire at a substation. We are lowering the risk that all the chlorine at your water treatment facility gets dumped at the same time, which literally happened in Florida. And it was only caught by one last sensor that someone had forgotten to update because the software attack on it had caused all the other sensors to stop putting their data out. Somebody actually tried to kill people in Florida by dumping all the chlorine in the system at once. That's risk. If that had happened, the insurance payouts would have been through the roof. Yeah, you bet. We can have a conversation with insurance companies about liabilities, about lowered risk. What does that do to premiums? Is that actually how this all gets paid for? Great questions. They do not have their heads wrapped around it. This is part of why we need consistent messaging on it.
Well, I was going to echo that thing. I've been talking to insurance companies. Anybody who's in Switzerland, like these guys and others, I went down to talk to folks over there. I also know folks in the open chain community. So there's one area of the Linux Foundation that you should be paying attention to, the open chain folks. I can put you in touch with them. They are driving a lot of this down the procurement process stuff. They are all legal guys who work for the very big companies, and they care about how the sewage gets into the bottom of the system. So you guys should be talking to those guys because they're already talking to people in that space. So come and talk to me after hand on that particular thing. But I know those guys well too.
Not a question, so I'm not going to repeat it, but good point.
Thanks for the amazing talk. I mean, you have expressed all the ideas that I had many, many years ago, and therefore I'm doing microkernels and not contributing to Linux. But the problem that I always had was how, I mean, here you are obviously preaching to the core. I mean, we are probably 100% on your side. Do you have some tips how to talk to the politicians about this? Because those are the policymakers. Those set the rules, ultimately.
Here, look, this is why this is the right time to have this conversation. Volt Typhoon, Volt Salt, Volt Flax are real. They're pervasive. I forget which country, I think it was someone in the US, just declared the Volt Salt to be a national defense emergency like over the weekend. People are scared. Volt Salt, by the way, that's pervasive, persistent attacks against the internet infrastructure. Volt Typhoon is going after the electrical grid. Volt Flax is, am I getting this right? Volt Flax is going after IoT, or am I wrong on that? Is that Salt? Yeah, that might be Salt. I'm jet lagged, so if I mix up some of those labels, I apologize. Right, but when you listen to the defense agencies, they're starting to go public, raising the alarm. That means there's politicians who've heard it who may not understand it, but they are open for maybe the first time to this conversation. And you're starting to see funding show up. And frankly, I see a couple hands up, but just a sec. Look back 10 years ago at DARPA funding, a whole lot of AI. Look right now at DARPA funding, a whole lot of automated reasoning, right? Well, and a lot of AI. And a lot of AI. Look, those are the two revolutions happening at the same time. Just a sec, Alistair. You had your hand up.
Yes, there's two things. One, while there's more fear of the consequences, fear alone only forces a decision, not an optimal decision.
Yep.
So we also need to provide information as to make the decision go into a direction that we would approve of.
Yeah. So fear alone is not enough. You have to have information on how to do things correctly.
And the second point with certification in particular, I think the large gap is that while in theory it is cheaper to maybe go via automated reasoning for a certification, in practice it is not, because there's not enough people trained in this, and so it's a big business risk. And I think the best way to address this would be if there's actual investment from the certification authorities themselves, so that they can offer more guarantees as to with what argument you can actually pass a certification, such that there's a practical, cheaper option via automated reasoning compared to what one could probably call practical.
Okay, I'll try to repeat it, but my adult brain only remembers one of the points, which was one of the problems with the certification angle is there aren't enough people who can do this. Right? And if there aren't enough people who can do it, how is it ever going to scale? You still can't require it. You're exactly right. Right? But think about mechanical engineering for a second, right? Yeah, I had to take the math classes. I took calculus. I took 3 semesters of calculus. That's not, you don't spend all your time doing the math as a mechanical engineer. You've got software that does that for you. You've got tools that do the fundamentals for you. You have to show that you used them correctly. You have to show you did the finite element analysis and the thermal analysis. You don't necessarily have to remember all the math down at the bottom. You have to say, these are the tools I use, and here's the evidence that popped out of them. What are you doing? This dude is making the tools easier to use. What's the job of those of us working on systems? It's not just to build a system that's based on formal methods, it's all the tooling around it. The tooling around it is almost more important. I mean, it's as important, but if it's not super easy to use, if I can't take someone who has no math background and have them build a system with evidence behind it, then we didn't do our job right. Right, so being an engineer does not necessarily mean you understand and can do all the math. It means you have to have tools that can do it, and that you're trained on how to use the tools, and you're able to generate the artifacts that you can hand to the regulator. And that's the only way we'll scale it. Go ahead.
In particular, this expertise must be there at the regulators. That's where I see the bigger gap actually. The industry could provide this expertise to a higher degree than certification authorities have the expertise to review these artifacts.
Yep. I'm tired. I'm not going to say it right. Part of it is training the certifiers as well, right? Absolutely. That's one of the bigger challenges here. But I'll give you a piece of point on the certifiers. Like, the thing I always do is I listen to what other people's pain points are. Not the pain point they say they have, but the pain point they actually have. I went to a very strange building in Poland a couple months ago, a former top secret Soviet research facility, which is like straight out of Stranger Things. It was weird. And I'm talking to this lady who's in charge of certification for electrical devices in Poland, and she's authorized to certify against the harmonized EU regulations. So when she says a device can go, it can work anywhere in the EU. And I ask her, hey, how long does it take you to certify a device? She goes, typically 12 months, except I can't do her accent and I can't say her name. I swear it's unpronounceable. So she says, 12 months for a device to go through certification. Okay, great. How much of the software in that device have you seen before, typically? And she says 80%. But there's no evidence. She can't prove it's the same software. She can't prove it's arranged in the same way. So they have to redo all of it every single time. I'm like, great. So when an update comes out to that device, how long does it take you to do the update? She goes, 12 months. Right? There's ways we can use the evidence with the formality at the bottom to cut the time through certification. The government people, the regulators, the thing they're facing with the proliferation of devices, they're screwed. They can't do it. They don't have the people, they don't have the time, they're going to be completely backed up, and they're not going to get anything certified. They need the answers. They need help, and that's the way you address them, right? You actually have to have the carrot as well as the stick. The carrot for the certifiers is you solve the update problem and the time through certification problem, which also ends up being a money saver to the people building devices.
Okay, we have time for one more question. What about hardware? Like with most like compute devices, so the longer you look, the more you find out that the hardware is actually also not that reliably doing only what the instructions tell it. Would you start also requiring that there, or how would you look at that?
So what about hardware? That's a great question. Hardware already tends to have more automated reasoning in its design. And we all have this common set of assumptions that the hardware works the way it's advertised to work, right? That's one of the core assumptions down at the bottom of the proofs. There's bugs in hardware. We got to address one problem at a time. I know of other companies that are working on provably correct hardware that are using cryptographic separation down in the memory bus. You look at what we did even back as far back as Xbox 360, there was hardware AES encryption engines on the memory bus where we encrypted every page of RAM with a different key and like actually set aside die space to hold keys, different encryption keys and SHAs of every single page of RAM. So if one bit flips, we would detect it and stop the clock. Right? That worked when you're trying to stop people stealing games. It's different on critical infrastructure. You can't just stop the clock. You have to be able to recover. It's a deep conversation. The hardware people are doing a bunch of things. The software people have to move ourselves forward. And then, yes, there's going to be a coming together between the two. Thank you.